Hope you can see my screen.
Yes, sir.
Okay, Ji. So today's class will be a short class. Maybe we'll be able to finish it by 10 o'clock. So this we are discussing the stress and stress transformation. And we had two classes, one with the analytical method of stress transformation and the other one with the more circle method of the stress transformation. Okay. Now, this was the whole course outline of this module 2. And in today's class, we'll talk about the strain transformation. Okay, and our last class will be related, which will be after it, will be related to relation between elastic constant and failure theories. Now, strain transformation analytical method. जी कोई मसला है? Any problem? एजाज आवाज clear राजी? Everything is okay?
Yes, sir.
Okay. So now stress can be calculated, but cannot be measured. There is a mistake here, so this not. Cannot be measured directly through experiments. So you cannot have a device that you install and then you calculate stress in a body. This you cannot do. Okay, you have force measuring devices, okay, and you have deformation measuring devices, but you cannot measure stress directly. Okay. In most complicated situations where the body is subjected to a number of forces that cannot be calculated accurately, the stress calculated is also not accurate. If you have such a case that you cannot find the forces which are acting on the body, there is a complex situation. Okay, so in that case you cannot calculate forces accurately, and so the stresses. So the stresses which you are calculated will not be accurate because the situation is very complicated, and that complicated situation cannot be idealized as a model so that you can get the forces and you can calculate stresses. However, strain in a body can be measured experimentally. So if you have such a complicated case, so you can install strain gauges. Okay, you can strain measuring devices on that body, inside the body or on the surface of the body. So you can then measure strains. So in such complicated situations, strain are measured and then converted in corresponding stresses using generalized law of stress-strain relation. You have studied the generalized equations of the stress-strain relation. We'll talk about that one also in today's class. So therefore, transformation of strain is equally important to the stress transformation. So that's why if you cannot measure stresses and you can measure strain, and strain is also a tensorial quantity, an important quantity, and the relation between the stress and strain is just an elastic constant. So if stress is a tensor quantity, then strain is also a tensor quantity. So that's why it is important to discuss the strain transformation also. So consider a 2D, two-dimensional strain field subjected to epsilon x, epsilon y as normal strains in x and y direction respectively, and gamma xy as shear strain. Okay, now let's discuss a case. Okay, where two-dimensional case where it is subjected to this one. So normal strain epsilon x and epsilon y are considered positive when they produce elongation, while gamma xy is considered positive if the 90 angle between x and y becomes greater. So that's the convention for this. So if let's suppose gamma xy is nothing, this is just the angular deformation. Okay, gamma xy is the angular deformation. If you have two lines, x and y, and let's suppose if before application of the law of the stresses, if the angle between those two lines is 90 degrees, and let's suppose if the angle changed to 91 degree, let's suppose, then this 1 degree, if you convert it into radian, is the shear strain. Okay, so if it produces such an effect, if that the angle is increased, like from 90 it becomes 91, so that is a positive strain, positive shear strain. And if the angle decreases, like if it becomes 89, then this 1 degree is a negative strain. Okay, so this increase in the 90 angle, increase in the angle is a positive shear strain, and decrease in the angle is a negative shear strain. And normal strain are, if they produce elongation, normal strain can be a contractor or a if the length of the element decreases, then that kind of a strain is known as a negative strain. So the same convention is applicable here also. Okay, so now we have a stress element whose dimension is dx and dy. Okay, and this stress element is subjected to these three components. This is a two-dimensional strain subjected to, this is epsilon x, epsilon y, and gamma xy. Okay, now if you just look to this element, okay, and we know the strain in the x direction, the linear strain in the x direction, the linear strain in the y direction, and the shear strain. We know this is by definition, this is the linear strain. If this, the original length of the element is dx, then this change in length will be epsilon x dx, because epsilon x is equal to the change in length divided by the original length. Okay, so this will be equal to the deformation in this element. And if in the y direction the strain is epsilon y, so this will be the deformation, and the shear deformation, this is the, the shear deformation. Okay, if you have the change in angle is, if it is gamma xy, okay, this is an angular deformation. Okay, so this will be gamma xy into dy. This angular deformation, this deformation will be gamma xy into dy. S is equal to r theta formula. Okay, so now if we have, if the element is subjected to these three kind of strains simultaneously, what will happen? This dotted shape is the deformed shape of this element. Okay, this dotted shape is the deformed shape of this element. Okay, now here you can see that there is a deformation, and let's consider a line OA, an inclined line OA, and we are interested in calculated the stresses. This is not a plane, this is an axial, this is a line in which we are interested in which we want to, in which direction we want to calculate the strain. Okay, so OA, this is supposed to be the x prime direction. Okay, so we want to discuss this. So what happens, so when you apply the stresses to this body, so due to the strain, this point A reaches to A dash because of this deformation. Okay, because of this deformation it reaches to A dash. So the total deformation is A dash. Okay, but a part of this deformation is a linear deformation, and a part of this is a shear deformation. Okay, now if you look to, this is the exaggerated, if you just see this exaggerated view here, you can see this one. So this is the exaggerated view of this. So this is point A, this is point A dash, and this is the deformation. Point A reaches from here up to here, so this is the net deformation. Okay, this is the net deformation. But we are interested in two deformation. One is the linear deformation, which is along this OA, and the other one is transverse deformation, because the linear deformation will give us, if we divide it, deformation divided by the original length will give us the will give us the linear strain in x prime direction. And this A dash, this line is perpendicular to this one. This A dash is a transverse deformation, and the transverse deformation actually gives us the shear deformation, a part of the shear deformation, not the total deformation. Okay, so now this change position is sum of what? This change position is equal to sum of this linear strain because of this epsilon x dx. Okay, so epsilon x dx is a linear strain because of the strain in the x direction. This is epsilon y dy is the deformation due to the strain epsilon y, and this is the deformation because of the shear. So this is gamma xy dy. This is the shear due to the shear deformation. Okay, so now we'll have to calculate, our objective is to calculate a double dash and a dash a double dash. A dash a double dash is the elongation in the element OA, and a dash will define the rotation or the angle beta of this element. This is, if you know, this small deformation here is this one, and this is the elongation from A to A dash. Okay, so our objective is to get an expression for this a dash and a double dash, a dash a double dash and a dash. Okay, so how can we do? So these are vector actually, and using this is a vector quantity because this is displacement, and displacement is a vector quantity. This is also displacement, this is also displacement. They are multiplied with the distance. Strain is not a vector quantity, strain is a tensor quantity. Okay, so from here up to here, if we resolve this force, this vector, this vector into its component along x prime and perpendicular to x prime, like y prime. Okay, so suppose we want to resolve this component. Okay, so this will be equal to the component, the x prime component of this along this a dash or OA, okay, plus this. So I've resolved this. So a dash, I'm sorry, this is a double dash a dash. I'm sorry, this is, yes, this is a dash, I'm sorry. This is a dash because there is a very small difference between the two. So this deformation is equal to this deformation because the angle is very small. Okay, so now we have a dash is equal to epsilon x dx cos component. If you take the cos component of this, so it will be in this direction. I haven't written just like I did in the case of the stress transformation, so I'm doing it directly here. So there is a component of this along this axis. Okay, so which will be epsilon x dx cos theta. Its component in this direction, since this angle is 90 degree, this is theta. Okay, so its sine component will be in this direction. So epsilon y dy sine theta. The sine component of this will be in this direction. And similarly, the cos component of this will be in this direction, but it will be a negative component because it is in this direction. Its cos component is in this direction. So a dash is equal to epsilon x dx cos theta plus epsilon y dy sine theta minus gamma xy dy cos theta. And similarly, if we take the other component, so we'll get a double dash epsilon x dx sine theta, the sine component of this, then the cos component of this minus epsilon y dy cos theta. The cos component of this will be in this direction. One is, if we resolve it into its rectangular component, so one component will be this and the other component will be in this direction. So this and this, so this component will be negative. So that's why epsilon y dy cos theta. And similarly, the component of this will be in this direction, in this direction, so which is opposite to this one. So it will also be a negative component minus gamma xy dy sine theta. Okay. Now the strain in this direction, is a dash divided by a. Deformation divided by the original length. Original length is OA. Okay. And beta, which is this angle, so beta is S is equal to, if we use the S is equal to R theta formula, so this one, this is equal to, this is the, and if theta is small, so beta is equal to a dash divided by, this is OA dash, AA dash divided by OA. R in this case is OA and S is equal to AA dash. So AA dash divided by OA. So this is equal to beta. Beta is not the shear strain, it's a part of the shear strain. Okay, this is not the total shear strain. We'll discuss this one. So where dx divided by OA, if we just say this is dx, this is dy, so dx divided by OA is equal to cos theta, and dy divided by OA, this is dy, divided by OA is equal to sine theta. So if we plug in the value in this expression, so epsilon x is equal to this value divided by OA, and beta is equal to this value, which is this one divided by OA. Okay, and if we replace this epsilon x by OA, epsilon x, dx by OA with cos theta, dy by OA with dy by OA with sine theta, okay, and dy by OA with sine theta, and similarly in this case, so finally you will get this expression. So epsilon x prime, which is the strain in the x prime direction, so this is epsilon x cos square theta plus epsilon y sine square theta minus gamma xy cos theta sine theta. And beta, which is the angular deviation, is epsilon x cos theta sine theta minus epsilon x sine theta cos theta minus gamma xy sine square theta. So we got these equation A and B. And in this equation, this is the strain, the normal strain, the linear strain in the x prime direction or in the OA direction, and beta is the angular deviation of line OA. Now to determine the linear strain epsilon and the angular deviation, the linear strain in the y direction, and beta, the angular deviation beta of a line perpendicular to OA, put theta equal to theta plus 90. Okay, theta plus 90, because if you want to, this is in x direction, so if you want to rotate to the y, so the angle will be theta plus 90. Okay, since this angle is 9, this angle is theta, if you have a line like this, so this angle will become theta plus 90. Okay, so just plug in the value theta plus 90 in this expression, so you will get epsilon y equal to this expression, and beta prime, which is the deviation of the other perpendicular line, will be equal to this one. Okay, so one is the deviation of OA and the other one is a line perpendicular to OA, so its deviation will be equal to beta prime, so this will be equal to this one. Okay, these deviation will always be in opposite direction. If one is moving like this one, this is moving like this one, so this will be this one, the perpendicular line will also be moving in the opposite direction, so they will always be, both of them will either cause shortening of the angle, or both of them will cause elongation in the element, in the angle, in the 90 angle. So if you want to calculate, so actually the 90 degree, this is a single line, so the 90 degree is composed by x prime and y prime. So if you want to get the angular deformation in x prime and y prime, you got beta is in the deviation along the x prime, a line along the x prime direction, and beta prime is the line along the y prime direction. So actual shearing strain is sum of these two. Okay, sum of these two, so the shearing strain is equal to the total change in 90 degree angle, which is the difference of beta, since one is, if one is clockwise, the other one will be counterclockwise. So their sum will be equal to actually their difference. So the shearing strain in x prime y prime plane will be beta minus beta prime, so which will be equal to this one. So you can simplify it to this equation. So we got expression for epsilon x prime, we got expression for epsilon y prime, and we got expression for gamma xy prime. Okay, so these are the transformation equation. These are the transformation equation. And now if we use the half angle formula, so we can convert this transformation equation to this one. Okay, we can convert these transformation equation to this one. So this is what this is: epsilon x prime is equal to epsilon x plus epsilon y by 2 plus this plus minus this. This is epsilon y prime is equal to this one, and this is gamma x prime y prime by 2 equal to this one. Now, if you compare these transformation equations, the strain transformation equation with the stress transformation equation, so they are identical in form. They are identical in form. These 1, 2, 3 equations are similar to the stress transformation equation. The only difference between the two set of equations is that we got tau xy in the transformation equation, so that is replaced, and that is not replaced with gamma xy, rather it is replaced with gamma xy by 2. Gamma xy by 2, here you can see gamma xy by 2, gamma xy by 2, here you can see gamma xy by 2, gamma xy by 2. The rest of the equations are same. The only change is that the epsilon is changed with now the sigma is changed with epsilon. So these are, since stress is also a tensorial quantity and strain is also a tensorial quantity, so same set of transformation equations are applicable for both the cases. They should be identical in nature, okay? But the only difference is this one. Now this half strain, this half shearing strain is known as tensorial strain. This is given a name of tensorial because this is used in the tensorial algebra, like this is the tensorial equations. So that's why this is known as a tensorial. This, when you divide the actual strain, the actual strain is known as an engineering strain. So this, if you divide this engineering strain with 2, so you get what? You get tensorial strain. So in the transformation equation, everywhere you will get the gamma xy by 2, not gamma xy, okay? Sometimes this gamma xy by 2 is replaced with epsilon xy. Sometimes this is replaced with epsilon xy, like the tensorial strain, this gamma xy by 2, just to get rid of this divided by 2, so it is replaced with epsilon xy. Okay, epsilon xy. So these are the transformation equation. And now you got the information, the engineering strain, the tensorial strain, and these things. Now the principal strains, just like we did in the case of the stresses, so the principal strain, the equation is same. The only difference is this gamma xy by 2. And the principal strains are also, the expression is same. The maximum shear strain, the equation is same. The only difference is this one. The maximum shearing strain divided by 2, not the maximum shearing strain. The maximum shearing strain divided by 2 is equal to this one, or in terms of the principal strain, it is equal to this one. Okay. So these are, if you just compare these set of equations with the stress transformation equations, so they are identical in form. Okay, they are identical. There is no difference if you just replace the gamma xy by 2 with tensorial strain, then totally they are identical. Okay, they are identical. Now, since when you measure strain, okay, then you will have to convert strain into stresses, or stresses into strain. So if you have, I've written this for a triaxial state of stress. If it is a biaxial, then sigma z will be omitted from these equations. Okay. So if you have a biaxial state of stress, so in the case of a biaxial state of stress, epsilon x is equal to this one. If you have the stresses are known to you, and you want to get the strain, and the state of stress is a 3-dimensional state of stress, then you will have to use this equation A. Okay, and this is the generalized form of the Hooke's law for a triaxial case. You discuss this in your mechanics of solid 1 in your second chapter, the strains. Okay, you discuss this thing. So this is, if the right hand side, on the right hand side you have the stress quantity, the left hand side is an independent variable of the strain in x direction. Okay, so these are the strains transformation equations. These are the stress strain relations. Okay, this is epsilon y, this is epsilon z. Now, if there is one thing you must note, that if you just omit epsilon z from this equation, then epsilon z is not equal to 0. Though the stresses are applied in x and y direction, so you will get obviously strain in x and y direction, but you will also get strain in the z direction also, because if you plug in this equal to 0, so because of the Poisson effect, you know this, what is Poisson effect? When you just apply a linear strain in the x direction, so the other two direction, if you elongate it, so the other two direction contract and strains are produced because of the Poisson effect. So this is the strain which is produced because of the Poisson, even if you put this epsilon z equal to 0 on this expression. Okay, so even if you have a biaxial state of stress, the strain field will be triaxial. Okay, the strain field will be triaxial, but the other two direction strains are dependent on these stress and these strains. Okay, if you know epsilon x, epsilon y, epsilon z is automatically known to you if you know the elastic constant. If you know the elastic constant, so the other two, the third strain component is known to you. Okay. Now, if you just invert these equations A, B, C, okay, so you will get these three equations. Now, in this case, now the strains are known and the stress component is unknown. So if you want to get epsilon sigma x, so this is the equation. So you will have to take care of these negative, positive sign, 1 divided by E divided by 1 minus u square and these things. Okay. Now, once again, if you plug in epsilon z equal to 0 in this expression, so it will not make that the stress in the z direction will be equal to 0. Okay, in the z direction, this is a case of a plane stress. If you omit sigma z, this is known as a plane stress case. Okay, and this is known as the case of a plane strain case. So if you have a plane strain case, the third dimension will also get a stress component. If you plug in this equal to 0, so you will not get 0 in sigma z. Okay, though there is no strain in the z direction, but there must be a stress in the z direction. Okay, and for the shearing strain, for all the shear strain in all direction, tau is equal to g into gamma. So E divided by 2 into 1 plus mu, this is G, and we'll discuss this relation between the elastic constant. So how G is related to this one, we'll discuss this in the coming class after E. Okay, so this is the stress, the shearing strain and the shearing stress converging equation. Okay. This G is known as the modulus of rigidity or the shear modulus. The modulus of rigidity or the shear modulus, just like the Young's modulus or the modulus of elasticity. Any question?
Sir,
G.
sir, in this relation, small v shows which theta?
Huh? Repeat your question.
Yes, sir. ये small v किस चीज को शो कर रहा है?
This is Poisson ratio. New. This is new, so I couldn't find the exact symbol for this one. So this is new, the Poisson ratio. Usually its value is from 2 to 0.45. So 0.5 is the extreme value. So it's not possible for common material to have a Poisson ratio of 0.5. So its value is around about 0.2 to 0.45 and these things. So for common cases, for steel, its value is 1 by 3.3, 3.3. For masonry, it should be 0.25 and these things. So this is an elastic constant. It should be experimentally determined. E, the modulus of elasticity. So for steel, you know, this is 200 gigapascal or 2900 or 29,000 KSI.
Okay, sir. Thank you.
Okay. Now let's come to an example. A state of strain is defined by, this is example 980. A state of strain is defined by epsilon x equal to minus 400 into 10 to the power minus 6. This is, strain is a very small quantity. So it is a unitless number because it is deformation per unit length. So it is a unitless number, and sometimes a unit is written like millimeter per millimeter or inch per inch. Okay, sometimes it is written, but it is not necessary. It's a unitless number. Okay, so there is a minus mean shortening. Okay, so this is a contraction, minus 400 into 10 to the power minus 6. Epsilon y is 200 into 10 to the power minus 6. And gamma xy is 800 into 10 to the power minus 6. If E is 200 gigapascal and nu is 0.3, modulus of elasticity 200 means it's a steel. Okay, determine the principal stresses and the stress components on the face whose normal is at plus 30 degree from the x-axis. Okay, plus mean a counterclockwise angle. Okay, so we'll have to calculate, one is the principal stresses and the other one is the stress component on the face whose normal is at a plus 30 from the x-axis. Okay, whose normal is at a plus 30 on a face. So this is basically we need to calculate stresses in the x, the strain in the x prime direction. Okay, now to determine the required stress component, first determine the corresponding strain component using the strain transformation equation. Strains are given, but the required is the principal stresses and the stress components. So you can do this question in two ways. Okay, but I'm first discussing, since we are discussing the strain transformation, so I want to do first the strain transformation and then convert those strains, this transform strain into the corresponding stresses. We can do vice versa. We can convert the strains into these corresponding stresses. We can convert these three components into the stresses using the stress-strain relation, the generalized form of the stress-strain relation. And then we can do the stress transformation. Since we are discussing the stress transformation, so I'm following the first method. So now theta n, the principal plane and stresses, this is the first component. Okay, he's just asking about the principal planes, the principal stresses, but I'm also locating it. So theta n is half of tangent inverse of minus this is equal to half of, if you plug in the value, you have 800. So 800 divided by 2. I'm not writing 10 to the power 6 because 10 to the power minus 6 from here will cancel with 10 to the power minus 6 from here. So I'm not writing that one. Okay. So divided by this one. Okay. Minus will become, this is 800 divided by 2 is 400 and this is 300. So 4 divided by 3 is 1.33. If you take tangent inverse of 1.33 and divide it by 2, so you will get the angle, so 26.56 degree. Okay, and it's a plus number. So plus mean counterclockwise direction. Okay, plus mean counterclockwise direction. Now, epsilon 1 and 2, the principal strain. So this is expression for the principal strain. So minus 400 plus 200 divided by 2 plus minus this. So minus 100 plus minus 500. So epsilon 1 is this plus this. So which is 400 into 10 to the power minus 6. And epsilon 2 is this minus this, which is minus 600 into 10 to the power minus 6. So I got the principal strains and its orientation. The orientation is not yet confirmed, but I'm not confirming because he's not asking me to locate the plane. You can plug in this value big in the transformation equation, in this equation, and to get whether this angle correspond to the this epsilon 1 or to epsilon 2. So you can confirm this, you can check this. Okay, I haven't done this. Now the stress component, I'm sorry, the strain component. This is strain components at plus 30. Strain components at plus 30. So this is the transformation equation, plus 30. So just plug in the value of epsilon x, epsilon y, and gamma xy, and theta is equal to plus 30. So you will get this expression. So if you simplify this one, so 596.4 into 10 to the power minus 6. So in the x prime direction, the linear strain is a negative strain. Okay, the linear strain is a negative strain. This is though not required, but for completeness, I'm calculating the linear strain in the y prime direction also. So in the y prime direction, this is when you plug in the same value, so 396.4 into 10 to the power minus 6. And the shearing strain, the tensorial shearing strain, gamma x prime y prime by 2 is equal to epsilon x minus epsilon y by 2 sine 2 theta plus gamma x y by 2 cos 2 theta. So this is, if you plug in the value, so finally you will get minus 59.8 into 10 to the power minus 6. Okay, minus 59.8 into 10 to the power minus 6. This is tensorial strain. Okay, this is tensorial shear strain. Now you got the strains, the principal strains, and the strain components in the along a plus 30. Okay, the strain components at an angle of plus 30. So you got those components. Now we'll have to convert using the transformation equation. We'll have to convert those into the corresponding stresses. So this is the equation. This is a two-dimensional strain case. So sigma 1 is equal to E divided by 1 minus nu square epsilon 1 plus nu epsilon 2. Plug in the value. So 200,000. I've converted this GPM to MPa because I want to get the stress value in the megapascal. So since that is a GPa gigapascal, giga is 10 to the power 9. So if you multiply that with 1000, so you get megapascal, 10 to the power 6. So this is the case, 200,000 divided by this. So this is the case. So you will get 48.35 MPa. 48.35 MPa is the stress, is the normal, is the principal stress sigma 1. Similarly, sigma 2 is epsilon 2 plus nu sigma 1, epsilon 1. Plug in the value, so you will get minus 105.49 MPa. And similarly, for the x prime, y prime, and tau x prime, y prime directions, so this is the relation, say that E divided by 1 minus nu epsilon x prime plus nu epsilon y prime. Plug in the value, you will get minus 104.9 MPa. And similarly, epsilon y prime is equal to this one. And tau x prime y prime, which is equal to E divided by 1 plus nu gamma x prime y prime by 2. Plug in the value, I plug in this value, this is directly this value in this expression. So this is minus 9.2 MPa. Minus 9.2 MPa. Okay. So these are the stress, the required stress component, the principal stresses and the stress components along the on a plane whose normal is at a plus 30 degree with the x-axis. Any question? Okay. Now, strain transformation Mohr circle method. The Mohr circle method of strain transformation is similar to the strain transformation method of Mohr circle, of stress Mohr circle. Is similar to the stress transformation. They are identical. The only difference is that instead of sigma we have epsilon 1, and instead of tau xy we have gamma by 2. And instead of tau, the shear stress, we have shear strain divided by 2. Okay, so this is the only difference. So we'll have to write like this. Okay, you will have to divide all the strain components or the shear strain components by 2. Okay, now here the for the strain Mohr circle, the center point is defined by epsilon x plus epsilon y by 2. The radius is defined by this one. The principal strains are defined by C plus R and C minus R. The maximum shearing strain by 2 is defined by R. And if alpha is the angle between the principal, the sigma axis and the required plane, then epsilon x prime is C plus R cos alpha, gamma x prime y prime by 2 is plus minus R sin alpha, and epsilon y prime is C. All these relations are same. Okay, here you can see this is a strain Mohr circle. This is the center point C0 with radius R. Draw this circle. This have coordinate C plus R0. This have coordinate C minus R0, just for the case of a stress Mohr circle. But here the C and R are defined by these equations, not by the stress the stress equations. This is C plus R, C minus R. Okay, so this is when you just locate this point. So this is the X, this is X plane. And on the opposite side, you have Y plane. On X plane, you have epsilon X, gamma XY by 2. And on Y plane, epsilon Y minus gamma XY by 2. And this is at, if you have a 2 theta angle, so this is when you rotate by 2 theta. So this is the X prime plane whose coordinate are epsilon X prime, gamma X prime, Y prime by 2. And when you just extend it on the back side, so you will get the Y prime plane, which is epsilon Y prime, gamma X prime, Y prime divided by 2. So the whole story is similar to the stress transformation. So that's why I'm not doing too much example on this case. Okay. Okay, the same problem 980. A state of strain is defined by this one and calculate these components. Okay, so this is the same problem. So Mohr circle, C is equal to this one. So this is minus 100 into 10 to the power minus 6. And R, when calculated from this expression, is 500 into 10 to the power minus 6. Okay. So just since this is minus 100, so move minus 100 to this side. Okay. Then open your compass equal to 500. Draw the circle, which is your Mohr circle. Show these points. So this will be equal to C plus R, and minus 100 plus 500 is 400, 0. C minus R minus 600, 0. Or C and R, so minus 100 and 500, or C minus R minus 100 and 500. So this is your Mohr circle. Okay, and you got this principal strain and the maximum shearing strain values from this expression. Now locate the X plane on this Mohr circle. Okay, so on the X plane we have epsilon X is minus 400 and gamma XY is 800. But we'll have to locate gamma XY by 2, meaning we'll have to locate 400. Okay, so minus 400 and plus 400. Okay, minus 400 and plus 400. So locate this point on this Mohr circle. So it's very easy. Move minus 400 this and draw a horizontal line, or move minus 400 and draw a vertical line. So you will get the point where it intersects with this Mohr circle will be your X plane. So this is your X plane with coordinate minus 400 and 400. If you extend it on the back side, so at this point this will be Y, and on the Y plane we have 200 and 400. So this is smaller and this is a larger value. So this will be 200, and here you can see, I'm sorry, here you can see that on the Y plane we have plus 200 and gamma XY, that will be gamma YX minus 400. So here you can see 200 and minus 400. So now you located your reference plane, which is the X plane. So this point defines the X plane. Okay. Now the next thing is that now you will have to locate the principal plane, and always move from the x to the maximum plane. You can move it to the minimum also, but it's good just to move to the maximum plane. Okay, so this angle is 2 theta n, and this angle is 2 theta s. Okay, so 2 theta n, how to get this 2 theta n? So first I'm going to calculate this beta angle. Okay, this is any intermediate angle. I can calculate it very easily. So if I take sine theta, so sine theta is this divided by this. Okay, so this is, I know this is 400 and this is the radius of 500. So 4 by 500 is 0.8. So beta is 53.1. So I got this beta value. So now it's very easy to get the 2 theta n. So 2 theta n is 180 minus beta, because the total this from here up to here is 180. So if you subtract this, so 180 minus beta, so 180 minus 53.1 is 126.9 degree clockwise. This is a clockwise angle. From x, your principal plane is at an angle of at a clockwise angle. Okay, now so theta n is equal to 126 by 9. So let me tell you that in the analytical method, when we calculated theta, analytical method, so this is the case when when we calculated 26.56. Okay, and here in the Mohr circle method, the angle is not the theta n is like 126.9 divided by 2 is not 26. It is greater than 26. But 53.1 divided by 2 is equal to 26.6. So actually, that angle 26.6 was basically defining the minimum principal stress. That was not defining, because at this location we did not confirm that whether this theta n of plus 26.56 has gone to this one, epsilon 2, or to epsilon 1. So when we do, if we check here, so we'll know that it will correspond to epsilon 2. Okay, it will correspond to epsilon 2. Now here, come to this position. So that's the reason why that is 126.9 clockwise and that was 26.6 counterclockwise. So both are same. One is moving towards the maximum one, the other one is moving towards the minimum one. The analytical equation you will have to check. It will give you a certain value, and then you will have to check whether it corresponds to the principal, the minimum one, or the maximum one. So, and here in the Mohr circle, it is clear. It is clear from the figure that if it's your well, if you are moving towards the negative one or towards the positive one. Usually we move toward the positive, to the maximum one. Okay, now what is 2 theta s? So 2 theta s is 2 theta n minus 90. 2 theta n minus 90 is 36.9. Alpha, which is the angle, then you will have to first then you will have to look at, I have done all the things directly here. Okay, because this is a figure and figure tells you each and everything. So this is in this figure. The next thing is, now you located, you calculated the principal strain and you located the principal planes. Okay, you located those. Now the next thing is to calculate the strain components at an angle of plus 30 degree. So this is your reference. You will have to look here, you will have to rotate by 60 degree from this. So you will get this green line. This point is actually your x prime plane. This is what? This is your x prime plane. And if you extend it on the opposite side, so this will be the y prime plane. Okay, this will be the y prime plane. Now here, this angle is, if this angle is alpha, okay, this angle is alpha, then what will be equal to this alpha? You know, this is what this total is 60 degree, and you know this is 53.1. So what is this remaining angle? Alpha is equal to 2 theta minus beta. This is equal to this one. So this is 2 theta minus beta, 60 minus 53.1 is 6.9 degree. So this alpha is 6.9 degree. So gamma xy by 2 is minus r sine alpha, okay, which is equal to minus 59.8, and epsilon y, since this is y, okay, this is making an alpha angle and this is y, so this is epsilon y is c plus r cos alpha, and c plus r cos alpha is minus 100 plus 500, which is 396 into 10 to the power 6. So 396 into 10 to the power 6. And similarly, you can get the value of epsilon. Let me do it here. Here in this case, since this epsilon x is on the opposite side, so that's why negative sign will come with this one. Minus, so this will be minus 596. It's taking much time inside. Okay. So now we have this one. So we got this point, this is y prime, and this is x prime. Okay, this is x prime. This value is not the shear strain, this is shear strain divided by 2. Remember, in the Mohr circle, the strains are divided by 2. Okay, so we got this one. So we got the shear strain, the tensorial shear strain, and the linear strain. Now we can convert this value, the principal strains and these strains, into component, just like we did in the previous case, and I've written it directly. So just using those generalized stress strain relation, then we already did that for the same transformation equation, just like this one. These are the transformation equation. So if you use these equations, so you will get these stresses. Okay, any question? Okay. Now coming to the last topic of today's lecture, the strain rosette. Strain rosette. Linear strain at a certain point of a body in certain direction can be measured using strain gauges installed at that point. Strain gauge is a strain measuring device. Okay, and usually electrical type of strain gauges are nowadays used. Okay, which are based on resistance type. There are two: capacitance type and resistance type. Usually, and most of the cases, we do have the resistance type strain gauges in our laboratory. All of the strain gauges, the load cells, and all these things are based on the resistance type of strain gauges. Okay, so the strain gauges are resistance type. Actually, if you have a wire, and if you its resistance is proportional to the length of the wire, you know this. Okay, and there is a constant which is known as the resistivity of this wire, which is constant. So the resistance of a wire is proportional to its length. And if you change the length of the wire, what will happen? Its resistance will change. Okay, its resistance will change. Now, let's suppose if you install a wire on a body, if you just paste it on a body with some means, what does that mean? I'll talk about that one. So if you install a wire on a body, and let's suppose if you are applying forces to the body and the body deform, what will happen? This wire will also deform because this wire is installed on the body. Okay, and if let's suppose if this wire, the two ends of this wire are connected to a certain measuring device like a Wheatstone bridge. You know the Wheatstone bridge. You have discussed that in your FSC. So if it is connected to the Wheatstone bridge, so that Wheatstone bridge can give you can measure for you the change in in the resistance, or the change in the voltage, which is associated with the change in the resistance. When you just change, when you elongate the wire, what will happen? Its resistance will change. So what will happen to the Whetstone bridge? In the Whetstone bridge, there will be a potential difference. There will be a change in the voltage. Okay. So if you can measure that change in the voltage, so you can relate that change in the deformation, or the deformation can be related to the change in voltage through some experiment. Okay, so that, like that, this single wire is just what this is a strain gauge. Okay, but since the sensitivity of a single wire, the change, since the change in the length is very small, so the change in the voltage will be also very small, so the signal will not be so powerful. So if you either just to use a long wire, so if you are using a long wire, so that will, if the strain field is variable, so that will not give you the actual value, that will not give you the instantaneous value, it will give you an average value on this whole length. Okay, but if you are interested in an instantaneous value, the strain value at a point, then you will have to keep the length of the strain gauge very small. Okay, so that's why, let me show you the figure. That's why here you can see, let me do it like this. So this is a strain gauge here. This is a plate, okay, a very thin plate. On this thin plate, this wire is arranged like this. This is the arrangement of the wire, and this is one terminal, and this is the other terminal. So here, its length is small, but its length is larger, but the size of this strain gauge is very small, because this is arranged in this form. Okay, so if you just change the length of this wire, so if there is a change, so the change will happen in this one, and this one, and this one, and this one. The total change will be sum of the changes in all these things. So here the change in length will be very high, and so is the signal, the voltage, the change in the voltage will also be very high, and the signal will also be very high. Okay, so this is the strain gauge format, and that can give you the change in length. And if you know the length of the strain gauge, then you can convert that change in length to the strain. Okay, divide that with this fixed length, because the length of the strain gauge will be fixed, so divide that with the length of the gauge, so it will it can directly give you a strain component. So accompanied with each strain gauge, there is a constant. Okay, there is a sensitivity measure. So there is a constant given. So when you are using a strain gauge with some data measuring, data logger like kind of thing, a Whetstone bridge, then you will have to give that constant. So the data logger will directly display the strain component. It will not display the change in the length, or the change in the resistance, or the change in voltage. It will directly display to you the strain component. Okay, because the rest of the thing, they are just converted into this constant. Okay, now, so linear strain at a certain point a body in a certain direction, and at a certain point of a body in a certain direction can be measured using a strain gauge installed at that point in that direction. ठीक है ना, आप उसी point पर उसी direction में just you install this gauge, it will give you the strain in that direction. However, one strain component in most cases is not enough to specify completely the state of strain stress at that point. If you want to know the exact state of stress at that point, that in most of the cases, one gauge will not be enough. In the case of axially loaded member, one gauge installed parallel to the direction of the stress is sufficient. If you have a member which is axially loaded, then you know that the strain is produced, the stress is applied only in the one direction. If you know this strain, then the whole story is known to you. In the case of a 2D state of strain, with known principal direction, two orthogonal gauges are required. If you have such a case, that the case is of a two-dimensional state of stress, and the principal orientation is known to you, the principal directions are known to you, then you can install you can have a two gauges, one installed along the one principal gauge and the other one along the other principal direction, and you will get the principal strength. So if you get the principal strength, then the strain field is also known. In general case of a 2D state of strain, however, 3 strain components, 2 linear and 1 shears are required to completely specify the strain field. 1 is enough for axially loaded. For if the principal direction are known, then 2 gauges are enough. But if the case is a general case of 2 dimension, that you need to have 3 strain components. Okay. And one thing, that shearing strain cannot be directly measured with strain gauges. You can measure, because if you have a wire and if the wire rotates, so the Wheatstone bridge will not give you any signal. वो आपको कोई signal नहीं देगा. Again, because the length of the wire does not change. But if the length of this is the reason why you cannot measure the shear strain. Okay, but we can indirectly calculate shear strain from the normal strain. Okay, so since you have 3 components, so therefore a combination of strain gauges known as strain roses is required to completely determine the state of strain stress. Okay, in the case of 2D state of strain, the strain roses consist of 3 linear strain gauges arranged at a certain predetermined orientation. Okay. In the case of a 2D strain rosette is the combination of strain gauges. This is either you make it as per from the individual strain gauges, you install it like this, or as rosette, a predetermined rosette from a company will come, and thus you will have to install it, and on that rosette you will be having 3 gauges. So there will be 6 wires coming out of that, and you will have to connect it, and it will automatically give you the 3 strain component. But those 3 strain component will be the normal strains, because the shear strain cannot be measured. How to get, we'll discuss this in the coming slide. Okay, so now coming to 45, there are 2 kind of 2-dimensional strain rosette. One is the 45-degree rosette, and the other one is a 60-degree rosette. They are most commonly used. Okay, 45-degree rosette and a 60-degree rosette. What is a 45-degree rosette? So this is the shape of a 45-degree rosette. It will be all of these gauges will be installed on a single plate. Okay, you will have to install it. So 6 wires will be coming, 2 from here, 2 from here, 2 from here, and you will have to install it. Okay, on the body, on the surface of the body, and then connect those wires to your Wheatstone bridge, to the data measuring device, which is known as a data logger or data acquisition system. Connect to that one, apply the constant to the data acquisition system. Okay, and then when you are applying loads to the body, so this data acquisition system will directly show you the strain produced at that location, the strain recorded by these gauges A, B, and C. Okay, A, B, and C. So if you have epsilon A, epsilon B, and epsilon C, if you have 3 gauges arranged in any orientation, we are not discussing yet a 45-degree rosette, are the linear strain components measured by the 3 strain gauges arranged at an angle of theta A, theta B, and theta C. If you have 3 gauges and they are arranged at an angle of theta A, theta B, theta C with x-axis, then epsilon A is equal to epsilon x plus y by 2, epsilon x minus y by 2. This is the transformation equation. Okay, so just plug in epsilon theta A in this equation for epsilon B, plug in theta B in this equation for epsilon C, plug in theta C in this equation. So this is what. So you are measuring these 3 things. Epsilon x, epsilon y, and gamma xy are unknown. You want to calculate these quantities. Okay. Now let's develop expression for 45-degree rosette. In a 45-degree rosette, the strain gauges are arranged in this way. 1 gauge is installed along the x-axis, 1 along the y-axis, and the other one at an angle of 45. Okay, so For 45 degree rosette, theta A is equal to 0 degree because this is along x-axis. Theta B is 45 degree and theta C is 90 degree. Okay, theta C is 90 degree. So if you plug in the value in this expression, epsilon A is equal to this one. So cos of 0 is 1 and sine of 0 is 0. So you will get this. Well, if you simplify this one, it will result in epsilon x. So it will give you epsilon x. The whole thing will be this one. So it implies that epsilon x is equal to epsilon a. So if you are measuring what you are measuring strain rosette will give you these three quantities. So epsilon a will directly be equal to epsilon x because this is installing in the x direction. And epsilon y, if you just plug in theta equal to 90 degree, so epsilon c, or c, theta is 90 degree. So this will be -1 and this will be 0. So finally it will be epsilon y, and epsilon y is equal to epsilon c. Obviously, this will obviously give you, because this is installed in the y direction. So obviously this will give you strain in the y direction. Okay. Now for this gauge, epsilon b is equal to this one. So this is cos of 90. Cos of 90 is 0 and sine of 90 is 1. Okay, so just if you simplify this one and plug in the value of epsilon x as epsilon a and epsilon y as epsilon c, so you will get epsilon a plus epsilon c divided by 2 minus epsilon b. So these a, b, c are the three equations. You are measuring three linear strain, but you are calculating epsilon x, epsilon y, and gamma xy by 2. This is a relation. You are calculating the shearing strain. You are measuring the linear strain in different three directions. Those using those transformation equation, you can you develop these equation and you are getting the three strain components required for a two-dimensional state of strain: epsilon x, epsilon y, gamma xy by 2. Okay. Now similarly for 60 degree rosette, this is a 60 degree rosette. This is epsilon a. Epsilon b is at an angle of 60 degree, and epsilon c is basically, if you just measure the angle with x-axis or with x-axis, it is making an angle of 120 degree. Okay, now with positive x-axis, this is x-axis, so it is this angle. If this is 60, then this angle will be 120 degree. So theta a is 0 degree, theta b is 60 degree, this is theta b, and theta c is 120 degree. You can arrange these strain gauges in this form also. Just look to the orientation: A, C, C, B, and B. Okay, so 120, 120, 120, but the orientation of the gauges are same. Okay, so either arrange them in this way or arrange them in this way. Okay, so it's up to you. If you have this as a more compact case, and it will require some more space. Okay, so the value, if you are installing it, let's suppose the main thing is that the dimension of the strain gauge should be very small so that you can get a point value. Okay, no? But as per requirement, there should be a minimum, which I've seen is that is a 5 millimeter strain gauge. Okay, usually it is 10 millimeter, 15 millimeter, 20 millimeter, even 50 millimeter, even 100 millimeter. Even for concrete, the gauges are very, the strain gauges are of length like 2 inch, 3 inch, 4 inch, you have about 2 inches, 3 inches, 4 inches, like 50, 100, 200 millimeter. Okay, so these are the strain gauges length. Now for this one, so theta is 0, theta b 60. So just plug in the value in transformation equation. So cos of 120 is 1 and sine of 120 is 0. So you will get 0. This is 0. Cos of 0 is 1 and sine of 0 is 0. So this is epsilon x is equal to epsilon a. And obviously this is installing the s direction, so it will directly give you the strain in the x direction. Epsilon b is equal to, this is the cos of 120 is -1 by 2 and sine of 120 is √3 by 2. Okay, and for epsilon c, This is cos of 240. Since this is the angle is 120, so this is minus 1 by 2, and sine of 240 is minus under root 3 by 2. Now, if you just solve these equations 2 and 3 simultaneously, solving equation 2 and 3 simultaneously, or adding these two equations. If you add equation 2 and 3, okay, so this will cancel with this one. This is minus and this is positive. So this term will cancel with this one. So you will left with epsilon b plus epsilon c is equal to this plus this, this plus this. So this plus this will epsilon x plus epsilon y, and this plus this will give you epsilon x minus epsilon y by 2. Since this is 2 times, so it will be, this 2 will cancel with this one. So if you add these two, epsilon x plus 3 epsilon y by 2, if you rearrange, in epsilon x is epsilon a. So if you rearrange this one, so epsilon y is equal to 1/3 of 2 epsilon b plus 2 epsilon c minus epsilon a. Okay. And if you subtract equation 2 from equation 3, so you will get, you will cancel, these two will cancel, and this will be epsilon c minus epsilon b will gamma xy by 2 into under root 3. Okay. And this is gamma xy by 2 is 1 over under root 3 epsilon c minus epsilon b. Now you got these three equations, equation 1, equation 4, and equation 5. Epsilon a, b, and c are the measured quantity, and epsilon x, epsilon y, and gamma xy by 2 are the strain components, the required strain components along x and y direction. Okay, so with this x and y direction strain, you can get any the principal strains, you can get the orientation of the principal strain, you can do it, yeah, in everything with this, if the strain field is completely known to you. Okay, now let's do an example. This is a problem 987. A 60-degree strain rosette attached to the aluminum skin of an airplane fuselage measures the following strains in micro-inch per inch. This is actually epsilon A is 100 micro-inch per inch, mean 10 raised to the power minus 6 inch per inch. Okay, so there is a 10 raised to the power minus 6 here. So epsilon A, which is measured by this 60-degree rosette, is 100 into 10 to the power minus 6. Epsilon B, which is measured by this gauge, is minus 200 into 10 to the power minus 6. And epsilon C, which is measured by this gauge, is 400 into 10 to the power minus 6. Okay, this A, B, C, it must be the A is this one, B is this one, C is this one. Okay, you cannot change these names. If the name are changed, then the formula will change. Okay, in the formula, these values will change. Epsilon B will change with epsilon C and these things. Okay. If E is equal to 10 into 10 to the power 6 psi, nu is equal to 1 by 3, compute the principal stresses and the maximum shearing stresses. So we need to calculate these things. So I'm doing, the problem is first I'll have to calculate the three strain components. These are the strain components, measured strain components, and the required XY and gamma XY components are that epsilon X for a 60-degree rosette, we know that epsilon X is epsilon A, which is 100 into 10 to the power micro-inch per inch. Epsilon Y, the expression is this one, we discuss this now, and is equal to 1/3 of this one, so it is also 100. And you calculate, so it is giving you 100 value. Gamma xy by 2 is equal to 1 under root 3 epsilon C minus epsilon B, so this is 346.41. So you got the three strain components, epsilon X, epsilon Y, gamma xy by 2. Now convert these three components, okay, into the stress components. Okay, you convert these three components into the stress components using the generalized stress strength relation. So E divided by 1 minus U square, this is the relation. So E 10 into 10 to the power 6 divided by this 100 plus this. I have multiplied this micro-inch per inch, so 10 to the power minus 6, I've multiplied it here. So this will cancel with this one. And when you simplify this, so you will get 1500 psi. So the stress in the x direction is 1500 psi, which is given by this strain rosette. Okay, the strain in the y direction, I'm sorry, stress in the y direction is equal to this one, which is also 1500 psi. And the stress in the y direction is given by this one, which is 2598 psi. 2598 psi. Okay, so you got the two normal stress component and the shear stress component in the xy plane. It should be. चार्जर लगा लेता हूँ. Okay. So now we'll have to, what I did in this case, I can solve the problem in two ways. One is, since the stresses are required, okay, so I can, from these strain component, I can calculate the corresponding strains, and then using these stress strain relation, I can convert those strains into the stresses. Okay, but here since I'll have to calculate it two times, because principal strain I'll have to calculate and then convert into the principal stresses and the maximum shearing stresses and then convert it. So it's easy just to first convert the strain into the stresses, and then using the transformation, the stress transformation equation, you can do what you want. Okay, so this is the case. So I've calculated the stress components. So the stress components are, so I'm using the Mohr circle method. So C is equal to sigma x plus sigma y by 2. So this is 1500. R is equal to 2598. Okay. So just plugging the value from Mohr circle. So this is Mohr circle. This is R, C equal to 1500. Draw a circle of radius equal to 2598. So this will be 4098, and this will be 1098. 1500, 2598. 1500 minus 2598. Okay, and this is your x plane. On the x plane, this is basically the state of stress, is basically the maximum shearing stress state of stress. Why? So I've told you that there is one identity of the maximum shearing stress, that the normal will be same. If the two normal components are same, like this is on the x plane, this is 1500, on the y, this is 1500. So this will be the maximum shear. Okay, this is the identity of the maximum shearing stress. Okay, so this is my 1500 and 2598. So this is my x plane, and this is 1500 minus 2598. This is my y plane. Okay, so my x plane, my y plane. So this is the angle from the x to the principal plane is 2 theta n is equal to 90. So theta n is equal to 45. Okay, theta n is how much? So the principal plane lies at an angle of 45 degree with the x plane. Okay, with the x plane. And the maximum shearing stress plane coincides with the x plane. Okay, the x plane is actually the maximum shearing stress plane. Now the last problem of today's lecture, problem 89. The three readings on a 45 degree strain rosettes are epsilon A. This is now a problem of 45 degree strain rosette. Epsilon A is 400 into 10 to the power minus 6. Epsilon B is minus 200 into 10 to the power minus 6. And epsilon C is minus 100 into 10 to the power minus 6. Let me copy the 45-degree rosette here. Okay. So this is 45-degree rosette here. Okay. So epsilon A, this one epsilon A, this is Meyer 400. Epsilon B, which is 45 degrees minus 200, epsilon C, which is at 90 degrees minus 100. If E is 200 gigapascal and mu is 0.3, determine the principal stresses and their direction. So epsilon X is equal to epsilon A. We know for 45-degree rosette. So 400 into 10 to the power minus 6. Epsilon Y is equal to epsilon C. Epsilon Y is epsilon C. So minus 100 into 10 to the power minus 6. And gamma xy is epsilon A plus epsilon C by 2 minus epsilon B. So 400 minus 100 divided by 2 minus 200. So 350 into 10 to the power minus 6. Now converting these strains into the corresponding stresses. Okay, these convert this into the stresses, the strain component to the stresses. So using the stress strain relations, there's an analyzed form of stress strain relation. So we got sigma x is 81.32, sigma y is 4.40, and tau of x prime y prime is equal to this shouldn't be prime quantities. So now calculate the center of the Mohr circle. So sigma x plus sigma y by 2, 42.86. The radius 66.17, and this is locate the center 42.86, and with 66.17 draw a circle. So this point is having, this is C minus R, so minus 23.31. This is C plus R, 109.03. This is maximum shearing stress 42 and is CR, so 42.86 and 66.17, and this is C minus R. Okay, now you have drawn the Mohr circle. Now locate the x plane. Locate the x plane. So this is x plane. This is at on the x plane. The stresses are the sigma x is 81.32. And the 81.32, and the shearing is 53.85. We know this. This is 53.85, and this is 81.32. So just from here, this is 81.32, and draw a vertical line. From here, 53.81, and draw a horizontal line. You will get this point. Okay, so this point is your x plane with coordinate of this one. Join this with the center and extend it on the back side. So you will get this coordinate. This is a y. So on y plane 4.4 and minus 53 points. So 4.4 here you can see on the previous slide. This is 4.4. Automatically it will give you 4.4. If you have drawn it to the scale, so it will automatically give you 4.4 MPa. PSI. I'm sorry. This is MPa or PSI. So I should change these units also to MPa. Okay. So this is the case. Now how to get this angle? This is 2 theta n from the x to the maximum. So this sine of 2 theta n is 53. This is of tau of 53.8, which is this one, divided by r, which is 66.17. So 2 theta n is 54.5 and theta n is equal to 27.2. Similarly, sigma 1 is C plus R. We already talked about this one. Okay, so we got the orientation of both, and we got the tau maximum also. Tau maximum will be this angle. So if this is for 54.5, then this will be 90 minus 54.5. Okay, 90 minus 54.5. So this is the end of today's lecture. So as I told you, so it's a short lecture. So I haven't including much problems because all the problems, the nature of all the problems are same. So if you can do one problem and you can do it yourself, you can understand each and every step of their problem, then you can solve all your group problem. Okay, उसमें कोई मसला जो है वो आपको नहीं होना चाहिए. आपकी तरफ से अगर कोई क्वेश्चन है तो आप पूछ सकते हैं. Any question? Okay, I'll try to upload an assignment today related to this transformation. So you will have to submit it just after the Eid. Okay, I'll specify the date, the submission date also, and there will be a quiz in the class after Eid. You can also make quiz bhi hoga. You can so that we complete our the quiz and assignments. So 2 assignment and 2 quizzes before midterm and 2 assignment and 2 quizzes after the midterm. Okay, so you will have yourself, and the quiz will be in the stress and strain transformation, and so as the assignment.
Excuse me, sir.
जी पूछें.
सर जो आप असाइनमेंट पोस्ट करेंगे उसकी ड्यू डेट मतलब
आपकी आवाज जो है वो बहुत स्लो और उसमें शोर भी आ रहा है. दोबारा बताएं.
सर आप जो असाइनमेंट पोस्ट करेंगे काइंडली उसकी डेट जो है वो मतलब मिड से मतलब 24 से थोड़ा पहले 22 या 23 रख लीजिएगा.
इसी तरह ही रखूंगा. मतलब वो आपको ईद के बाद जो है, ईद की छुट्टियों के बाद जो है वो 3-4 दिन उसको करने के लिए मिलेंगे. ठीक है
सर. और सर
जी
सर 4 असाइनमेंट और भी दिए तो थोड़ा एक्सटेंडेड डेट.
क्या करूं?
एक्सटेंडेड डेट दे दे.
आपने अगर नहीं करना है ना तो आप मतलब आप एक्सटेंडेड डेट में भी नहीं कर सकोगे. ठीक है, मेरा असाइनमेंट इतना लेंथी तो नहीं होता, घंटे 1.5 का असाइनमेंट होता है, जिसको मतलब आप बहुत आसानी के साथ जो है वो कर सकते हैं. उसमें टाइम इतना जो है वो नहीं लगता, उसमें तो 1 दिन भी काफी होता है. ठीक है, जब नहीं करना होता तो बस वो तो नहीं करना होता ना, जब करना होता है तो बस वो मतलब उसके लिए ये टाइम भी अच्छा खासा है. ठीक है
सर जो क्विज है काइंडली वो भी अगर आप फ्राइडे या सैटरडे को कर दें मतलब थोड़ा टाइम मिल जाएगा हमें.
नहीं, उसी क्लास में होगा ना, बस नहीं टाइम तो बस उसी क्लास में हमारा मतलब ये ईद जो है वो कल या परसों ईद है ना. ठीक है ना, तो हफ्ता आपको जो है वो ये 2-3 दिन जो है आपकी ईद में लग जाएंगे. ठीक है, और 4 दिन उसके बाद आपको मिल जाएंगे. सो मेरा नहीं ख्याल कि ये 3 दिन जो है मिल जाएंगे, तो 3 दिन तो काफी टाइम है. आपका तो ये रनिंग सेमेस्टर जा रहा है ना, आप इसको रनिंग सेमेस्टर के तौर पर ले लें और प्रॉपर इसको प्रिपेयर करें. ईद पे इतना जो है वो बस 1 दिन आपके लिए काफी है, आप अपनी प्रिपरेशन करें. ठीक है ना, एक्सटेंडेड टाइम हम नहीं रख सकते हैं. ठीक है ना, क्योंकि मतलब वो उसको मैनेज करना, क्योंकि आपकी क्लासेस जो है वो बाकी भी होती रहेंगी, क्योंकि उसमें कोई गैप तो है नहीं. ठीक है ना, तो उसको उसी वक्त जो है वो उसमें जो है वो क्लास में करना पड़ेगा. ठीक है, जी बताएं और कोई क्वेश्चन.
थैंक यू.
अच्छा, आप यू विल हैव टू डू योर असाइनमेंट. मैं बार बार बता रहा हूँ ना, पिछले आप अपने जो है वो बाकी जो आपके क्लास फेलोज हैं, जो बाकी सेक्शंस के हैं, जिनको मैंने जो है वो मैकेनिक्स ऑफ सॉलिड 1 पिछले सेमेस्टर में पढ़ाया था, उनसे फीडबैक जो है वो आप ले लें, आप अपने असाइनमेंट को खराब ना करें, डू इट योरसेल्फ, ठीक है ना। मैंने अपने जो है वो मैं खुद भी उसको देख रहा हूँ और अपने टीचिंग असिस्टेंट को भी जो है वो बताया हुआ है कि जो भी plagiarized assignment होगा, so we'll have to discard that assignment. So plagiarism is not acceptable in any case, ठीक है ना। There is an objective of this course, and the objective is that you should learn the basic rules of mechanics of solid 2, and you should be able to deal with any kind of a case of mechanics of solid 2. So if you are unable, okay, if you are just doing copying it and you are using plagiarizing your assignment, so it will not solve the objective. So you should be very careful. ठीक है जनाब, ओके जी, चलो फिर